All right, hey there, everybody. Welcome back to another installment of Introductory Econometrics. So, in this installment, we're going to begin a series of lectures on specification. Before we get into specifically choosing the correct variables, let's introduce this idea of specification error. When we talk about specification error, we're talking about the specification of our hypothesized relationship of our independent variables to our dependent variables. In other words, what do we think, what variables do we think explain variations in our dependent variable? And then what do we think the relationship of those variables is, movement in those independent variables, is to movement in the dependent variables? And so this involves really a lot of choice on our part as how we want to set the experiment up. It involves choosing the correct independent variables. It involves choosing the correct functional form and choosing the correct stochastic error form. Okay. Now, in this video, we're going to be focusing just on the first of those, the choice of the correct independent variables. But a failure in any one of these is going to result in what's called a specification error in your regression output. Okay. So to start off with, and the most common and seemingly obvious, but in practice not very obvious, error that one makes is omitting a variable. So omitting a variable that has important explanatory power regarding movements in your dependent variable that simply is not in your regression equation. Okay, and when we do this, when we omit an important variable, it effectively creates bias in the remaining equation in the vast majority of cases, and we'll talk in just a little bit about the specifics of why that is. What happens, if we can imagine like a situation, you learn about planets when you're a kid, right? There's this sort of rotation stuff up over here. You think about planets and gravity, right? You hear people talk about where there must be a missing planet or something like that, and they say, okay, well, gravity appears to be pulling this scenario or these planets in this direction, or these stellar bodies. And that's how I kind of think about this, right? Is if we have something that's sort of missing, right? If there's a missing variable rather than a missing planet, what's going to happen most of the time is we're going to observe movements that don't fully make sense, and they don't fully make sense because there's a thing missing, right, from what we're trying to explain. So what ends up happening is the remaining independent variables get pulled in directions that they really shouldn't get pulled, because there's a thing that's important that we're not including in our regression analysis. And that pull that happens in most cases is referred to as omitted variable bias. Okay, to see why this is, consider the following over here. Let us say that we have this true regression equation. Okay, so this is the true relationship. You say, how do we know the true? Yeah, you don't know the true. Okay, we'll come back to that later. Okay, say that this is the true relationship between the dependent variable and the two independent variables x1 and x2, okay, as well as the error term and so on. But for whatever reason, we construct the following hypothesized relationships. Again, this true relationship, we construct this hypothesized relationship here, where we hypothesize that movements in our dependent variable y are a function simply of x1, omitting the true independent variable x2. Okay, and we've noted this on the error term here, in that this error term is going to have problems, right? Okay, because this is what's going to result. Okay, so if we omit this true independent variable from a hypothesized relationship, then what is going to happen is that the value of that independent variable is going to get caught up in this false error term. So the true error term plus the neglected or omitted relationship ends up getting captured in this false error term, or resulting from the misspecified equation. Okay, because of course this variation, this true variation, doesn't disappear when we run our regression, right? It's still out there in reality. It's just we aren't incorporating it into our model. And so what ends up happening in the very best case scenario is that the value of that movement gets caught up in this error term. Beyond this, right, so beyond that, the value that omitted variable getting wrapped up in the error term. Now, if x1 and x2 are totally uncorrelated, right, okay, as in the above relationship, then the impact of x2 will get fully incorporated into the error term, right? However, if x2 is in any way correlated with x1, or if we have more independent variables in the true relationship, right, then those variables will be biased and correlated with the error term. Why? What's going on here? Okay, let's say that we have x1 and x2, and x1 and x2 are, say, wealth and income. Okay, now we can be reasonably sure that those two variables have some correlation between each other. In other words, as income goes up, wealth probably goes up, and as wealth goes up, probably income goes up too. The latter may be less certain than the former, but there's going to be a relationship between those two variables. In other words, they're not going to be wholly independent of other variables within the model. Okay, what's happening in that case then is, if as we omit, say, wealth, right, or better, easier, let's say we omit income, right, and we explain like current spending, y, as a function of wealth, right? Well, you and I know that current of income, right? And so some of that, so there's going to be some variation in expenditures that is really a true function of income. But because income is moving in its direction similar to wealth, what our estimated beta coefficient on that is going to show us, right, is going to be showing us that variations in wealth now are moving along with, or appear to be explaining, variations in spending, right? When in reality, it's perhaps both wealth and income, right? And so now we're over-attributing variations in spending to wealth and under-attributing variations in spending due to income, right? So those variations in spending are getting over-captured in this beta associated with wealth. Okay, so we're biasing our beta coefficient associated with wealth as a result of omitting income. And anytime you have any kind of collinear relationship between any of your independent variables, okay, which is going to be almost always, right? It's unfortunate, but it's the nature of reality, right? Anytime you have those collinearities to any degree, right, omitted variables are going to bias your remaining estimator. Now, how then do we correct for that? Well, it's not an easy thing to do, right? One would be, sort of might be drawn to the idea, we'll just start adding things, right, and see what happens to the test results. So let's keep working towards a higher R squared or something like that. And that's maybe not the best approach, right? Similarly, you might think like, oh my gosh, that one variable is really, it's causing me trouble. Its sign looks bad or even in the wrong direction. Let's just eliminate it, right? Well, in some cases you may do that, right? But if you're talking about a significant variable or one that's theoretically important, right, then probably you're going to be doing more harm than good. Okay, so let's think about that. The possibility of removing or adding variables to attempt to mitigate problems associated with omitted variable bias. Well, you can sort of run through some diagnostic steps to try to start thinking about what we really should be doing in this case. The first thing we would want to be thinking about is have we included all the theoretically significant variables? So, for example, if we're looking at like a demand style relationship, have we included all the prices, which would seem obvious, right? But so we would have included the explicit price, but perhaps we're missing some implicit prices associated with consumption. So if we're thinking about taking a vacation or something like that, maybe we've remembered to include the ticket price of going on a vacation in our model, but maybe we've neglected to consider other implicit or opportunity costs like lost wages or something like that, right? So starting to think, sort of brainstorm through the basic economic theory associated with the problem you're trying to resolve is a good sort of first step to diagnosing this, right? And whether you really have all the variables that probably should be there based upon theory. The second thing we want to sort of think about when we diagnose these, right, are the t-tests associated with our independent variables. Are they showing significance, right? So, if a variable is showing significance, then that's at least for the time being, that's something that probably needs to stay in there. If it's not showing significance, we need to start thinking about why and what's going on there. If we know something is theoretically important, but it's not showing significance, that's a good indicator that we're missing something. So, for example, if like the price of a thing isn't showing significance, then we're probably missing something associated with the cost of that. Now you might say, well, maybe it's just perfectly inelastic, right? So people will buy it no matter what the price. Yeah, that might be true, right? If you're talking about a life-saving medicine and it turns out price really has no impact on demand, yeah, maybe. But for most things, price is going to have some impact on the quantity that people demand, right? So we need to think carefully about that idea. Thirdly, in terms of the diagnostics, we would want to think about what's going on with the R squared here. Now, these are in order of importance, right? So start with theoretically sound, significance, right, and then R squared. Okay, so take a look at your R squared, your adjusted R squared, and what's going on there? If your R squared is like 0.4 or something like that, but you might think, well, we're only explaining 40% of the variation here in the movement of the dependent variable. That's probably a pretty good indicator that you're missing something important, right? If you're explaining less than half the movement in your dependent variable, almost certainly you're missing something important, and you need to start thinking about what variables really should be added. Okay. Then finally, the last thing we want to look at is testing for bias. When we add or remove variables from our specified model, do the estimated coefficients on our remaining independent variables, they bounce around a lot. Okay, so there's a companion video to this actually where I run a bunch of regressions and I show you this happening. If you're in this class, right, that video is right next to this one in your to-do list. But if you're a regular person watching this, take a look at the playlist, and I have a video on sort of the applied version of this lecture, right? But so let's say you've got that wealth and income thing again, right? And when you add wealth, the coefficient on income changes significantly. The estimated coefficient on income change. Well, that's a pretty good indicator that was an important missed omitted variable, because what was happening is a lot of the variation in spending, using our recent example, was actually attributable to income and not just wealth. And when you added income, a bunch of the former explanation of changes in spending attributable to wealth now got slotted over to income. Okay, so you see those estimated betas moving around a lot as things get added or pulled in. Pretty good indicator that if it's not there, right, it was an omitted variable. Okay, now that we've talked a fair bit about omitted variables and the problems as well as some of the corrections, let's move over to the other side of this, irrelevant variables, right? So as we said, you can have too few variables, but you can also have too many variables, right? And when we include independent variables that have really little to no bearing upon variation in a dependent variable, we create a similar problem to omitted variable bias, except for in the opposite direction, right? So consider, over there, consider the true regression equation where the variations in y are really only attributable to x1. But we hypothesized the relationship where movements in y are attributable to x1 and x2, right? Well, when that happens, when we do that, right, our error term becomes misspecified in a manner very similar to what we saw with omitted variable bias, or excuse me, when there's an omitted variable, right? And so here, we have this, over there, right? Okay, we have that our hypothesized error term, E double star, right, ends up being the true error term minus the falsely specified variable x2 times its estimated coefficient. Okay. Now, it's similar to omitted variable bias. If x2 is totally uncorrelated with any of our other or remaining independent variables, then this isn't a huge, it's wrong, right? But it's not a huge problem, right? But if the much more likely possibility that x2 is somehow correlated with x1, right, then this misspecified error term and the inclusion of x2 as a variable is going to bias our estimator on x1. In other words, very similar to before, if we have that x2 in there, our beta, estimated beta associated with x2 is going to pull some of that attributable variation in y away from x1 and stack it into estimated variation in x2. Okay, so in this case, we are going to end up under attributing variations in y, assuming positive correlation, right? We're going to end up under attributing variations in y to x1, right? Because we're attributing some of that variation falsely to x2. So we want to ask ourselves, in this case we just had like x1 and x2. Does theory tell us that x2 should be in there, or not, right? Or were we just trying to sort of throw everything at it and see what sort of sticks, right? The t statistic, right? Now it's certainly possible that in this situation of including irrelevant variables, that we find that the t stat associated with with x2 is not significant. But again, not guaranteed, depending upon how highly correlated those variables are. If x1 and x2 are highly correlated, then we could end up with x2 appearing to be statistically significant in terms of explaining variation in y, when it isn't really in reality, right? It's only because it moves nicely with x1. All right, to try to imagine this, let's say that we had, we were attempting to explain, a movement in a string, right? I like this. I'm trying to think of like some silly sort of thing, right? Like, or like maybe like a clock. Okay, what a clock, chiming noon or whatever. So it's a clock at the university, chimes noon, ding, 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 12 times. And we hypothesized that the chime in the clock is a function of the clock's mechanics as well as birds crowing. And that's our x1 and x2. So clock mechanics, x1, birds crowing, x2, right? And it turns out that any time the clock chimes, the birds crow or something like that, right? Well, when we run that regression, right, it's going to appear that birds crowing is statistically significant in determining, when it's the top of the hour or when it's 12 noon, because it's happening together, right? But that's not correct, right? It has no bearing upon, if you could clear all the birds out of there a quarter to the hour, the clock would still strike noon, right? And so now your attributable specification, right, your attributable impact of your independent variables is biased across all of them, in this case of only being two, right? Just due to spurious correlation between your independent variables. Okay. So in that case, theory would tell us that clocks probably don't depend upon birds, and if we eliminated that variable in that case, we would actually end up with a stronger explanatory relationship, stronger hypothesized relationship, and stronger estimated relationship than we had before. To see this is an example from your textbook, right, which is the student month text, just for people who are sort of picking this up midway through. Let's say we have this hypothesized relationship. We're going to say that we estimate that coffee, so coffee hat, right, the price of coffee is a function of a few different things, right? And so we're going to say it's a function of this variable BC, which is the price of British Columbian coffee, right? Okay, so PBC, price British coffee, which is the coffee we're concerned with. So this is the price of the item. And then also PT, or the price of tea, a substitute good. Okay. And YD, disposable income. So if people get richer, right, they buy more coffee. And we run the regression, and we get these test results, and we get these these estimated values of beta, and solving out for variations in the price of coffee. Now, in this case, we get R squared of 0.6. Looks reasonably good. Our test statistics there show significance on price of tea and disposable income, but not on the price of coffee, right? So in other words, our first regression results suggest that price has little to no bearing upon the amount of coffee people buy. Okay, and so we think, oh my gosh, it's statistically insignificant. Let's just eliminate it and see what happens. So we go ahead and eliminate, the price of the coffee, and we rerun the regression, and we get these results over here. Okay, price of tea, the estimated coefficient on that has moved a little bit. Price of disposable income, it's moved a little bit, and indeed our R squared is actually improved by a tiny bit, right? So on the surface, right, it would look like, well, this is better. Coffee must be highly price inelastic. It doesn't matter what the price of coffee is. People buy it no matter what. Well, yeah, right. I mean, that may be true for some folks, right, who really need their coffee. But I mean, I really like coffee. Like I like coffee a lot, right? But it's not true for me, right? Like if you made coffee cost, $40 a pound or something like that, I'd really have to think my coffee consumption. For sure, I'm not going to buy as much. And so that sort of sniff test about theory, right? So just like the basic economic theory that suggests that something's wrong here, something's wrong. Okay, so we can't just kind of leave it at this, right? We need to, maybe it turns out that this is right, but definitely we need to do more work to figure out what's going on here. So let's say we think about this a little bit, and oh my gosh, we think, oh, maybe there's different kinds of coffees. So before we had a substitute good, right? Maybe we didn't include all the substitutes that maybe we should have. Okay, and so we run another regression now with a few more prices, and I'm going to use a cursor this time. I know I don't like to use a cursor on these things, but okay. So we're going to include the price of Colombian coffee as well as the price of British Columbian coffee, and also the price of tea and disposable income. Okay, so we've got a different type of coffee, our coffee, that we're actually talking about buying, right? And the price of another substitute, okay, and disposable income, right? And now we run that regression, and whoa, here it comes back. Okay, all the variables are now significant, and they have the sign that we would expect. Okay, so it turns out that as the price of Colombian coffee goes up, right? People buy more British Columbian coffee, but as the price of British Columbian coffee goes up, people buy less of British Columbian coffee. Okay, all right, so it makes sense now, right? Oh, what's going on here is that there are a bunch of different coffees that have different prices, right? And if some coffees go up in price, there's a lot of other coffees. That was what was causing this statistically insignificant result before, as well as this weird sign on this, right? People were moving back and forth between different types of coffees. If the price of our coffee goes up, people buy less. But if the price of other coffees goes up, people buy more of our coffee. Oh, okay, all right, so it makes way more sense now, right? Like the whole story kind of syncs up and they're like, oh yeah, that's clearly better. All right. We run those diagnostics again, right? And if we start to get that good feeling, like, oh, this is kind of, well, I should be careful there, right? We don't want to do this all by feelings, right? But you can kind of feel when your understanding of the situation is improving at the margin, right? And so here, this is a nice little example of, and as you go forward in doing econometrics, right, you're going to have these moments all the time where it's just you're banging your head against your wall with something. The sign is wrong. It's not significant when you think you should. That's just a really good indicator that something's wrong in your specification, right? That you may be including a variable that you shouldn't be, or you're not including a variable that you really need to be including, and you need to dig a little deeper into all this to figure out what's going on. We're getting towards the end of this, right? This is getting quite long. I apologize. Again, it needs to be said, we never know the true specification, right? So you're never going to know exactly everything, every independent variable that explains changes in your dependent variable. I shouldn't say never, but if you do, right, that's another problem, right? It's not going to happen very often, right? And so you're always kind of, the true relationship is always kind of hiding there somewhere, right? And so you're always kind of, shooting towards it, and you're making alterations in what you're trying to do based upon something that you don't know perfectly, right? So, you have to understand that it is somewhat an imperfect process, and this is why conversations amongst researchers is very important to understand what other people are thinking and the directions other people are going when they make corrections in course, when they make alterations to specification. It's important for reflection and consideration. It also should be said that that while sort of shopping for regression results is really not good econometrics, as we mentioned in a couple other videos, there is no right number of regressions to run in any given test. Sometimes you get it right off the bat, right, and other times you end up changing some things. In both the example here, the coffee one as well as the wealth and income one I mentioned earlier, those are legitimate mistakes, right? I mean, it's not like we were setting out to get some specific result, right? We just made an error in specification in our initial hypothesis, and upon further reflection, right, we were able to find theoretically valid reasons why other variables should be included or not included, and when we did that, we found improved results. So if the results and the alteration to the model are consistent with knowledge within the field and with theoretical understanding, right, then you're probably on the right track and you're really improving things. All right, well, that's it for this time. We'll be talking about specification for the next couple lectures. I hope this has been helpful, and I hope to see you again in the next one. Take care, everybody. Cheers.